My name is Jan Hammaker. I'm the Program Director of Drive Sweden, and if you haven't noticed, this event is sponsored by Drive Sweden. I know that many of you are already very active in the program, but for those who may not be, just let me remind you that we are a strategic innovation program co-financed by the Swedish government. Our task is to sort of coordinate what's happening in their domain of connected and self-driving vehicles in Sweden. Right now we have over 80 partners that are all committed to designing the future mobility. And one of our latest pilots, if you haven't been to Chalmers yet, go up to the Chalmers campus to try the self-driving shuttle that will run there through the month of May. But let's move on to today's topic. And I'm inclined to borrow a phrase from Netflix. If you followed Dave Letterman, he has a show, and my next guest doesn't need a presentation. And this almost goes for Steve. But let me mention a few things. He lives in the very heart of the Silicon Valley. He can walk to Waymo's office. He's been teaching many of the people that are now considered as rock stars in the self-driving business in his profession at UC Berkeley. He's one of the key people behind the most important conference on automation, AVS, Automated Vehicle Symposium. And if you haven't attended that one yet, you should go this year. Last time in San Francisco, next year it'll be Orlando, much first place to be in the middle of summer. But of course, the most important thing with Steve and why we were happy to have him here is that he's probably the world's most experienced researcher as far as automated driving systems. We've been meeting on and off at different conferences for over 25 years. But this is the first time we are in Sweden at the same time, so I'm really happy to welcome you here, and we're looking forward to enjoy your presentation.
Thanks so much. Pleased to be here, and I'm pleasantly surprised that you've got similar weather to California. That's not what I was expecting when it's coming to Sweden at this time of year. So I'm going to talk about some of the practical challenges we face in trying to deploy highly automated vehicles. And this is motivated in part by seeing a lot of what's written in the media and on the internet that I look at and say, that's not true. And most of what's been published on the subject is wrong in a variety of different ways. So I find I'm often the truth squad that has to go around saying, well, it's not exactly like what you read in the media. I'm going to begin with some historical overview of how we got to where we are right now. And then I'm going to talk a little bit about terminology, because the terminology in this field is a terrible problem and leads to a lot of misunderstandings. And then I'll focus on why connectivity is really critically important for getting to automation. And talk about a couple of the key challenges that have to be met, that have not been met yet, and are going to take a long time to be met. And that's on perception technology and safety assurance. And those I see as the big technical impediments to getting to higher levels of automation. And then I'll conclude with some discussion about the market introduction process and how long it's likely to take for this to work through. And it's going to be a lot slower than most of the media accounts would lead you to believe. I also find when I talk, especially with younger audiences, people think this began with Google. Or maybe it began with the DARPA challenges, and I have to say, well, no, I started working on it when I was a graduate student, and that's 40 years ago, 45 years ago, and it was already a well-established field well before then. So this has a much longer history.
And now we see an enlarged section of 1960s express motorway.
1960s.
Along the ledge of this beautiful precipice, traffic moves at unreduced rates of speed. Safe distance between cars is maintained by automatic radio control.
Automatic radio control maintaining safe distance. And remember, 1939, we're in the era of vacuum tubes, not even solid-state devices. So the vision was already there in 1939. It was being portrayed as a 25-year vision for the 1960s. The actual technical work began around 1950. This was still a vision in 39. But the team at the RCA Sarnoff laboratories that developed the NTSC television system then started working on vehicle automation about 1950. And they got together with General Motors and worked with General Motors on a variety of vehicles.
Roger, Firebird 2, move to electronic control strip in center lane.
Notice the aircraft analogies here.
Synchronize your speed and direction.
Check. Maximum speed first.
Autopilot. Elon Musk did not invent the term. That's a gas turbine powered vehicle. That's why it makes that high pitch whine.
Well done, Firebird 2. You're now under automatic control. Hands-off steering.
See the concept of the foldback steering wheel? Even mid-1950s. Not something new, even though some people like to claim that they've invented it more recently. Now, that's nice and simple. There's nobody else on the road. So they've got the road to themselves. Here's a test track experiment from General Motors 1960.
The driver still operates accelerator and brakes. But look, no hand. This leaves the driver more relaxed to enjoy the trip and free to more attention to other driving responsibilities. Two antennas on the car pick up low-frequency radio signals from the varied cable and transmit steering directions to the car.
So automatic steering
now,
control.
This car, traveling out of its lane and under manual control, is switched to auto guide.
Maybe not the smoothest way of doing that, but again, 1960s, so we're looking all analog, and it's probably vacuum tube electronics back in the trunk of that car, not even solid state. 1964, another World's Fair.
Vehicles electronically paced, travel routes remarkably safe, swift and efficient. Towering terminals serve sections of the city, make public transportation more convenient, provide ample space for private cars, and from a lower level, covered moving walks radiate to shopping areas that are now truly marketplaces of the world.
So the vision has been there for quite a while. This was the highlight of the 1964 World's Fair, and I remember going and seeing that exhibit several times myself.
This experimental car is equipped with a computer and designed to be driverless.
1977, this was at Ohio State University.
Have been working on the project for 10 years, and they feel that cars like this one may be on the nation's roads by the year 2000.
Maybe on the nation's road by the year 2000. So we have this 25-year moving horizon where it's always going to be 25 years hence. And that was a research program that began in the mid-1960s, continued to about 1980. And again, all analog control. I think the last project they did in 1980, they did something digital. But so this happened long before the kind of modern control approaches. Here's one, a European one. This is from Professor Dickmans at the University of Bundeswehr in Munich.
Wouldn't it be nice on those long motorway trips to just sit back, relax, and take your hands off the wheel? Well, maybe one day you'll be able to, because this purely experimental van is driving along now at about 35 kilometers an hour, totally automatically, using only this ordinary camera to see where it's going. Well, since it seems to have everything under control, I can nip in the back and show you how it works.
So this is a BBC program, that's why we've got the English accent. And
Well, at the moment, the back of the van is packed with control equipment that will eventually just fit into a small box. And up here is the output of the camera,
So-
the van's eye.
computer vision technology, not that much different in the fundamentals from
information in a picture like this.
computer vision today.
Just to identify the road. That is
So we don't need to go through the whole thing. And then some of the work that we did at PATH, this was our demo in 1997. We've got 8 vehicles, all driving automatically. We took about 1,000 people for demonstration rides on those test vehicles. The driver simply engaged the system at the beginning of the run and disengaged it at the end. They're doing automatic steering, they're maintaining close separation. In this case, it's 5.5 meter gap. And we have automatic lane changing, they change positions with each other, all with demonstration riders. And again, level 4 automation, this was in 1997. Notice it's on a section of highway that was not shared with any of the other traffic, however. So it's physically segregated from the rest of the traffic. So the point is, there's been a lot of work done in this field over many years. We're building on all of that work today, but we still have a long way to go. Now, the terminology we deal with often gets in the way of understanding. And I often see media reports that talk about driverless, and in the vast majority of the cases, they're not driverless. There's a driver in the vehicle. The role of the driver has changed from what it would be normally, but they're not driverless. Self-driving is the term that Google invented and that they've been pushing for use of this, which doesn't really tell you a whole lot about what it does. And then we have this troublesome word autonomous that turns out has 4 different usages. So whenever somebody uses the word, I don't know what they mean. I have to ask follow-up questions. What do you actually mean about it? The 3 of those definitions don't even correspond to what's in the dictionary. Robotic, another one of those confusing, misleading words. So if we're going to try to understand what we're talking about, there are 3 central issues that we have to be clear about. One is, what's the role of the driver? What's the role of the system? Second is, how connected are the vehicles with other vehicles in the infrastructure, and what extent of active cooperation is going on with the other vehicles in the infrastructure? And finally, what's the operational design domain? And I'll explain that in just a minute. SAE defined the levels of automation based on a series of questions that we have to ask about the relative roles of the driver and the system. I'm not going to go through those in detail because Jan told me everybody should be understanding that already, although I actually find that in the vast majority of cases people misunderstand these and they don't use them correctly. So just as a point of information, a vehicle without pedals and a steering wheel is not level 5. Vehicle without pedals and steering wheel could be level 4, could maybe even be level 3. It's only level 5 automation if it can drive everywhere that people can drive under the full range of conditions in which people are able to drive. Operational design domain. And this is an important concept within the SAE classification scheme because this defines the specific conditions under which the automation is capable of operating. That could mean the type of roadway, the range of speeds, or the kind of traffic conditions in which it's operating. It might mean a geofenced location that's been very carefully mapped by the developer. Could be the range of weather conditions and lighting conditions. Could be whether you've got some special cooperative infrastructure, either electronic infrastructure or physical infrastructure modifications to make it more suitable for automation, or the condition of pavement markings and signage. I've had discussions with regulators who think they're going to specify operational design domains, and I have to say, no. You as a regulator cannot specify that. That comes from the manufacturer. That's based on the limitations of the technology, the sensors, the software that's embedded in the vehicle. Every vehicle automation system will have a different operational design domain from every other system. And examples of some of the systems that would exist at each of the levels. Of course, level 1 systems are widely available on cars already. Level 2 systems becoming more widely available, and mostly in high-end vehicles, are now starting to get down into more mid-range vehicles. At level 2, the driver must still continuously be monitoring the driving environment and be fully engaged in driving. At level 3, the driver may temporarily disengage, but has to be prepared to take over when the system needs help. Level 4, it can maintain safety even if the driver doesn't do anything, but it is restricted within a defined operational design domain. And only when we get to level 5 is a system that can operate everywhere without the need for driver involvement, but a driver could still take over and choose to drive a vehicle that's equipped with a level 5 automation system. There is a new update of that document that will be coming out within the next month or 2. It's just working through the final stages of balloting in SAE right now, and that will provide a little bit more explanation to try to overcome some of the misunderstandings that have gone on with the previous version, in which people have misinterpreted what the different terms mean. I'd now like to get into the issue of connectivity, because I think that's going to be critically important to get to the higher levels of automation. A cooperation, vehicle-to-vehicle, vehicle-to-infrastructure, is a way of augmenting sensor data so that you can get more and better data about what's going on. I refer to the autonomous vehicles, that is the unconnected vehicles, as deaf-mute drivers. Those may be systems that can see what's going on around them, but they can't talk to other vehicles, they can't get messages from other vehicles either. So without having that active connectivity, we're actually going to make traffic flow worse than it is today. It's going to be less efficient, and may be less safe. That's still undetermined. And I will show you some data to back up that contention. The cooperative vehicles are the ones that can talk and listen to each other, and as well as seeing. And we've emphasized a lot the use of 5.9 gigahertz dedicated short-range communication, known as ITS-G5 here in Europe. With that type of information, vehicles can communicate information about their performance and their operating condition directly. So for example, if a braking command has been given to a vehicle several vehicles ahead of you, that command can be communicated to your vehicle, so you know that braking is coming even before that vehicle that got the braking command started slowing down. That's really important to get quicker response and to get more stable response in traffic. You can also get information from vehicles that are not within the line of sight of your sensors, so you can get that information from vehicles that are further away. The vehicles can negotiate with each other to get cooperation. For example, things like merge coordination or lane change coordination, which can help significantly in improving traffic flow. And the communication and coordination makes it possible to run the vehicles closer together without sacrificing safety. So overall, we can get a much wider range of performance if we've got vehicles communicating in cooperation with each other. And there's some functions that can only be implemented if we've got communication, like the cooperative adaptive cruise control, the automated merging, allowing vehicles to coordinate their operations at a merge junction, the multiple vehicle platoons, and especially truck platoons, where we're critically dependent on having vehicle-to-vehicle communication. On the vehicle-to-infrastructure side, we can also use speed harmonization, which a traffic management center can communicate a desirable speed to the vehicles using the section of highway so that they can all travel at that speed to reduce traffic flow disturbances. If you've got vehicles approaching a congestion queue, they can get information about that slowdown in advance so they can start slowing down rather than waiting until that congestion queue is within the sensor range. Because for available sensors, you can't detect that soon enough. If you're traveling at highway speed, by the time your sensor has detected stop traffic ahead, you're into a panic stop situation rather than a gradual, smooth deceleration. And we can also do things like precision docking of buses and bus stops or precision control of snowplows. Yes, we do have snow in California in the mountains, and we've done automation of snow blowers for use in the mountains in California. Well, what do we need to get this vehicle-to-vehicle communication effective? We have to have a system that will provide that information frequently enough that it doesn't impede our vehicle dynamic responses. And that means in the range of 50 to 100 millisecond updates. And we have to have enough data communicated at that point that we can represent the motions of the vehicles adequately so that the vehicles behind know how to respond. And we probably need some emergency condition flags and maneuver commands. If, for example, we've got a cooperative platoon that's going to do a lane change, then all the vehicles need to know about the lane change response. We also need a little bit of information about hazard alerts and the logic for negotiating cooperative maneuvers. It's not a huge amount of information. In fact, the work has just begun within SAE on defining message sets that would be needed to implement this so that vehicles from different manufacturers could cooperate with each other. And I expect it's not going to be a terribly large message. It's very well suited for the 5.9 gigahertz DSRC communications. When we start going into vehicle infrastructure and infrastructure to vehicle, we need to make a distinction because they're not the same. So if we're going infrastructure to vehicle, then one of the most important messages is the traffic signal status. So that is, what's the current phase of the traffic signal? And if we know how much time is left on that phase, we also want to communicate that to the vehicle so the vehicle approaching the signal knows how much time it has left to get through on the green. And that's typically a 100 millisecond update, at least based on traffic signal controllers in the US. If we're going to provide speed advisories, this would be the way of doing that, a recommended speed for a particular section of roadway. We can also provide information about traffic hazards. For example, not just a congestion queue, could be an object that fell off a truck that's in the roadway, could be a pothole on the roadway, could be other traffic conditions hazards like that that need to be communicated to the vehicles. And maybe there would be emergency software updates, although that one is fraught with all sorts of issues in terms of cybersecurity. From the vehicle to the infrastructure, all of those vehicles can serve as traffic condition probes. They can be telling the traffic management center what they're doing, what their speed is, and that can provide information that's very useful for traffic management purposes, finer grained information than you would get from roadside sensors. Vehicles can also request priority of traffic signals, and this is particularly important for trucks or buses that might be given a higher priority to go through a traffic signal. So if they can communicate to the traffic signal system, then they can get that priority. Most of these are not as time critical as the vehicle-to-vehicle message. They can be satisfied by 3G or 4G cellular, and also by the DSRC communications. Notice I didn't mention 5G. So I don't think 5G is needed to be able to do this. And I know I sometimes hear the 5G advocates saying, oh, well, we need 5G in order to get to automation. No, we can do automation without 5G. But what kind of advances are needed? For 5.9 gigahertz DSRC, we still have to prove the management of the congestion on the communication channel in the highest density traffic environments. Those have been experimented with up to a few hundred vehicles. It probably needs to get to more hundreds of vehicles to deal with the most congested conditions. And we need some extensions to the messages to support the vehicle-to-vehicle cooperative control aspects. If somebody wanted to use 5G for this, well, the first thing is show it can actually scale up to serve the needs of the entire traffic network while all the people in those vehicles and in the nearby buildings are using their 5G mobile devices for their bandwidth-intensive operations. If they're downloading movies or playing video games, those are all trying to use the same communication bandwidth that's needed for the vehicle safety applications. Does that scale? And is there an acceptable cost and business model for the vehicle users? They're not going to have to keep paying every month for their essential vehicle safety applications. They just buy it when they get the vehicle. Now, I mentioned this fact that the communication and connectivity is going to be really critical to get good traffic flow. So I want to show some of the reasons behind that. We've done a lot of work in traffic simulations to try to estimate what the impacts would be on traffic of the connected and automated vehicle capabilities. In order to do that, we have to have several different capabilities. The first is we need to have really high fidelity representation of the way drivers drive. And that means the car following and the lane changing behavior of the drivers. The standard default models that are available in traffic simulation packages, I don't think have the level of fidelity that's needed to do this. We've had to develop a new generation of models to be able to represent those things. And we have to be able to calibrate those models for what's going on in specific traffic corridors. As we discovered, if you go from one corridor to another, there are enough differences in driver behavior. You can't leave the parameter values the same. Then we've done some really detailed models of adaptive cruise control and cooperative adaptive cruise control car following to be able to represent that car following dynamics. And in this case, we've derived them directly from experiments on full-scale vehicles. There are a lot of car following models that have been published in literature from all around the world, and we look at the results. The results you get from those models are scattered all over the map, and you can find a paper that has any conclusion you want to see depending on who wrote the paper. But what we discover once we start looking at the models is most of them are so oversimplified, they don't represent the way real vehicles behave. And I'll show you an example from test data coming up in the next slide. We also need to model the traffic management strategies that you implement to try to take advantage of the capabilities of the connected and automated vehicles. And then if we want to estimate energy consumption, we have to be able to process the vehicle speed profiles in order to generate energy consumption as well. Now the results I'm going to show you are for level 1 automation, but they actually apply to higher levels as well, because the car following and the lane changing are not going to be noticeably different when we get to higher levels of automation. So we're going to begin with autonomous adaptive cruise control. That is a basic production adaptive cruise control that just uses a forward-looking sensor, but no vehicle-to-vehicle communication. So we did a set of experiments. We took 4 production adaptive cruise control vehicles, We programmed a speed change profile on the first one, and you see on the plots here, the speed's on the left, the acceleration's on the right. The test data from the experiments on the vehicles is the upper plot in each case, and our simulation model, which was derived from the test data, is shown on the lower one. So you see on the left there, the speed, accelerate, decelerate, they're ever increasing levels of acceleration. On that last transient, we're doing a 1 meter per second squared acceleration, 1 meter per squared deceleration of the leader. The fourth vehicle, you look up there, is decelerating at 3 meters per second squared, while the leader was decelerating at 1 meter per second squared. We have an amplification of a factor of 3 in the acceleration, and that response was delayed by 5 seconds. This is because of the car following dynamics of the adaptive cruise control system. The fact that it takes the sensor a while to recognize what's going on, and the logic is built in such a way to smooth out the driving, so we get a significantly delayed response. This is a traffic shock wave in the making. In fact, when I rode in that fourth vehicle, I said I'd turn that system off. Any sensible driver would have turned that system off instead of continuing to use it, because the behavior was so bad. So this is a string instability, and by the way, this was published back in 2014, the paper in which we derived the model from the test data. So we take the model that's represented in the lower part of the plots, and we put that into the traffic simulations. Now, we took the same test vehicles and made a cooperative ACC out of it. So we added the vehicle-vehicle communication. We redesigned the controller to make use of that information. And now you can see all the vehicles following the same speed profile. The acceleration's very well behaved. So we put the cooperation on, we've eliminated that traffic flow instability. Without it, it's traffic flow unstable. It's going to be a lot worse than with human drivers. So now we take those vehicles and we start putting them into a simulation where they're mixed with normal manually driven vehicles. And this is a set of cases for market penetrations of cooperative ACC vehicles in increments of 20%. So the 0% case is just manual driving, all the vehicles driven conventionally. Then we start adding more and more cooperative ACC vehicles, and you see the parabolic profile as we gradually get a higher throughput. The different lines here represent different on-ramp volumes. So the uppermost line, the green one, is when we have no on-ramp traffic, and you can see there we've gotten up to almost double the lane capacity that we would have with manual driving. But as we get more and more on-ramp traffic, that improvement gets lower and lower, because additional on-ramp traffic creates more conflicts at the merge point. We go through the same analysis with the autonomous ACC without cooperation. As we add more and more ACC, it gets worse. And that's because of the unstable car following. So now we see our capacity of that highway section goes down as we get more and more ACC vehicles. And that would happen if we had higher levels of automation as well. If we put unconnected automated vehicles out in the traffic flow and we got to a significant fraction of the traffic flow, our congestion is going to get worse. We have to study those simulations very carefully. I'm going to show the animation here of a merge junction. The upper one here is with all manual driving. So this is just the basic driver model. The colors correspond to the speeds. So green is basically free flow speed, and then as it slows down, it goes to orange and yellow and red. This is a case where we've added enough on-ramp traffic that we've actually exceeded the capacity of that merge junction. So 7,500 plus 900 is 8,400. That's right around the flow breakdown point. And you can see we're starting to get congestion show up, more and more of those vehicles going orange and red. You also see there's a lot of lane changing going on. Drivers in the right-hand lane approaching that merge are going to start moving to the left to avoid the conflicts with the entering traffic. But there's a great deal of complexity embedded inside that simulation to represent both the car following and the lane changing decision making by those drivers. This took a year and a half, 2 years with a couple of postdocs working full time to get to the point of having a simulation that actually predicts this sort of behavior in a realistic way. We have to get to that point before we can start looking at what happens when we add adaptive cruise control or cooperative adaptive cruise control. So here we've got all the vehicles equipped for cooperative ACC driving, and we're adding the same volume of on-ramp traffic. And we're only going to see a very slight slowdown in this case, because with the cooperative ACC, we're able to get vehicles closer together. We're able to damp out some of the vehicle following disturbances. And here you see they're still almost all in green, a little bit of yellow and orange right at the lane changing point where the entering traffic gets into the mainline traffic stream, but those disturbances go away pretty quickly. And that's why we saw the higher volumes of traffic that we could get with cooperative ACC. If we tried this with the adaptive cruise control, this would have gone red almost instantly. So that's why I'm not showing an animation with the regular adaptive cruise control. We would have had to ramp the traffic volume down in order for it to be able to continue if we were doing regular ACC. Oops, let's go on to the next one. So part of this is to also estimate what's the fuel consumption going to be. What's this going to do for fuel economy? So here, these plots are time on the horizontal axis and location along a corridor on the vertical axis. And what we've done is inserted some traffic at the on-ramp. The colors here represent the rate of fuel consumption. And on the left side, you can see with all manual driving, we've got some slowdowns and some disturbances that are causing increased fuel consumption. On the right side with the cooperative ACC, there's just a little bit of increased fuel consumption right at the merge location where we've got some lane changing happening. Same traffic volume in both cases. When we wanted to compare with adaptive cruise control, we actually had to ramp the traffic volume down to avoid total mess. So this is actually with a lower on-ramp traffic volume. Now you can see the cooperative ACC on the left, the regular adaptive cruise control without vehicle-to-vehicle cooperation on the right, and you can see much significantly increased fuel consumption associated with that because of all the instability in the car following based on the regular adaptive cruise control. We also wanted to look at traffic along a real corridor. So the traffic flow model was calibrated for a freeway corridor approaching downtown Sacramento, California, where we were able to get some pretty good data. And here we're going to see the plots for 6 different levels of cooperative ACC market penetration. This represents the morning period from 4 a.m. to 12 noon. So the morning commute peak is the part where we see the colors changing. This upper left one is today's condition, the baseline condition with all manual driving, and then we've added 20% increments of cooperative ACC. Well, the first 20% of cooperative ACC actually makes things a little bit worse, and that's because of that low market penetration. They can't make use of the cooperative capability. Most of those vehicles are operating in a conventional adaptive cruise control mode because they don't have a cooperating vehicle right in front of them. By the time we get to 40% though, the congestion is significantly reduced, and then you see we get to 60, 80, and 100%, the congestion is pretty much gone away. So this shows how having that cooperative capability with the automation can help us relieve the traffic congestion in a real freeway corridor. So I wanted to switch from some of those traffic impacts to some of the technical challenges. And why is this going to take a while to get to the higher levels of automation? I'm going to begin with the perception technology challenges. Well, in order to have that vehicle drive out there in mixed traffic, it's got to be able to perceive any relevant object within the path of the vehicle, because the vehicle is going to have to make driving decisions based on that. It doesn't only need to perceive what the objects are, but it needs to be able to predict what the future motions of those objects are. There's a big difference between a pedestrian standing on the side of the road and a pedestrian stepping out into the path of the vehicle. So you have to add perception plus prediction in order to have a usable system. And that means you've got to deal with vehicles, pedestrians, bicyclists, animals, any moving objects that might get into the path of the vehicle. And I think it's pretty clear it's got to at least match the perception capabilities of an experienced human driver under all of the environmental conditions within its operational design domain. So this is where that operational design domain comes back, because now we have to say, what is the set of conditions in which we can prove that that automation system is at least as good as a human driver? It's not going to be true under all conditions. It'll be true under some limited set of conditions. And now the key thing is, how limited is that set of conditions? From what I can perceive, there's a growing consensus, there's no silver bullet sensor that's going to answer all of those needs. And it's probably going to be necessary to have radar and LiDAR and high precision digital mapping with localization and video imaging and wireless communication. Because they have different strengths and weaknesses, different complementary capabilities, and you've got to have fallback capabilities. If one of those is disabled for any reason, whether it's an internal fault or an environmental condition, you better have enough other systems on board to keep the system safe. And I'm not sure there's any way of short-circuiting that need based on the current state of the sensor technology. So you get the raw sensor data, then you have to assess the threats that actually exist to the vehicle. So the vehicle has to be able to detect and respond to every real hazard, that is a hazard that could cause a dangerous situation, including ones that are not so easy to see, like the negative obstacles with the deep potholes, or something that's inconspicuous but could still be dangerous, like say a brick right in the tire track of the vehicle. So if the vehicle's going to hit that brick, that's going to be bad news. But it also needs to ignore things that are easy to see but are kind of harmless. Like could be a metallized balloon, could be a paper bag in the road. How do you distinguish between a paper bag that's just empty, it's not going to be any harm, versus a paper bag that's got something heavy and hard inside of it? Those are serious challenges to the sensor technology, because you've got to be able to satisfy both. And how do you set the threshold sensitivity for decision-making on the system so that you get to zero false negatives, that is, you don't fail to respond to something dangerous, and you also have to have near zero false positives. You don't want the vehicle to suddenly brake or swerve around something that's totally harmless. This actually leads into a safety versus functionality trade-off, because you've got this false positive versus false negative dichotomy. In order to have safety, you've got to have virtually zero false negatives, and you've always got to detect the real hazards. But within the limitations of technology, that means you either have to keep the speed pretty low, so the sensor has enough time to collect enough samples to actually recognize the threat. And if there's any doubt, if you don't really know, stop the vehicle, because that's the way you avoid harm. On the other hand, functionality is not very good if the vehicle's stopping all the time or if it's going really slowly. So in order to have good functionality, you're going to have to avoid the spurious emergency brakings, and you're going to have to maintain a high enough speed to provide a useful transportation service. Satisfying both of those is really hard. And I think it's going to be quite a challenge to get to the point of having vehicles that are capable of delivering a viable transportation service while maintaining safety. So have to deal with a wide variety of external hazards. We don't have to go through all of these. Everybody's got their catalog of many different types of hazards the vehicle is going to encounter, and a wide range of environmental conditions you have to deal with. In the US, just about everybody is doing this in the Sun Belt, where you don't have to deal with snow and ice, and yeah, that helps simplify things quite a bit. If you're going to do it here in Sweden, you're going to have to deal with snow and ice also. The other thing you can do is simplify the environment, reduce the operational design domain by having some cooperative infrastructure. And the examples here, the upper left, are a couple of personal rapid transit systems that run in tracks that are physically segregated from the rest of the traffic, so they don't have to deal with other objects, they don't have to deal with other vehicles. So that's Masdar on the left and Heathrow Airport in the upper center. We can run in a segregated highway lane like our 1997 demo, which is in the upper right. So you see the only vehicles that are in that section of the highway are the ones that are equipped with automation and communication. They don't have to deal with the unpredictable actions of other drivers because you don't have any of those other drivers sharing that space. And the lower pictures are from the City Mobile project. That was a demonstration in La Rochelle in France a couple of years ago, where they were operating in a mixed environment with pedestrians and with other vehicles. They had to communicate actively with the traffic signal, so that, for example, at a place where the vehicle crossed a roadway where other vehicles were driving, it triggered the traffic signal to give a red light to the other traffic so that they wouldn't overlap. And to be able to interact safely with the pedestrians, this was speed limited to 7 kilometers per hour. Well, 7 kilometers per hour, you can almost walk as fast as the vehicle is going. I was tracking it, taking video, and I stayed with it for quite a while before it got ahead of me. So how useful a service are you going to provide if you can only go 7 kilometers per hour? So that's some of the trade-offs. The big challenge in all of this is how do you get to an acceptable level of safety? And I use the US traffic safety statistics, say, as a baseline, because I have yet to hear anybody say it would be acceptable to put an automated vehicle out on the road that's less safe than drivers are today. So when I use the US statistics, I find we've got 3.4 million vehicle hours between fatal crashes. Now, that's a really big number. I had to convert it into years in order for it to make sense. That's 390 years of continuous 24 hours a day, 7 days a week operation between fails. And if we look at injury crashes, it's still 7 years of continuous 24/7 operation. Think about those in terms of your laptop computers and your mobile phones and all of these other modern devices that depend a lot on software. What's the likelihood that those are going to go for 390 years or even 7 years of continuous operation without ever giving you a little hourglass or a little wristwatch symbol that says it's not ready to give you the answer you want, or without just locking up? Because if you got the hourglass symbol or the wristwatch symbol and was driving your car, you crashed. That's just not acceptable. So these existing traffic safety numbers set a very, very high bar that has to be matched. I contend nobody knows how to do that yet. Now, these numbers are going to keep improving over time because we're going to have more and more collision warning and collision avoidance systems built into the vehicles. So just normal drivers doing their driving are going to get safer and safer through use of those collision warning, collision avoidance systems. And by the way, Sweden, the numbers are going to be probably twice as large as the numbers for the US because your traffic safety statistics are quite a bit better than ours. So we're saying, 800 years or 15 years of continuous operation between serious events. How are you going to do that? And how do you know you got there? How much testing do you have to do to show that the automated system is at least as safe as the humans that it's replacing? The RAND Corporation did a study a couple of years ago. They did some statistical analysis and showed the amount of mileage you had to drive was many times larger than the amount that you've got in the statistics, just to prove with some level of statistical confidence that you actually got the system notably safer. Well, that would be unaffordable to do in practice. So we got a challenge of what's the process you're actually going to go through to verify that you've reached that safety level. What evidence do we have about safety of the existing automated vehicles? Well, the one set of evidence we've got is in California, the companies that are doing testing on public roads need to report their disengagements when the test driver had to take over from the automation system because of a safety-related challenge. Those are reported every year. By far the best of them is Waymo, which is the former Google. And their report for 2017 testing was released a couple of months ago. It's a little bit ambiguous about their exact approach, but at least what they reported for the previous year's analysis was not the actual disengagements, but it was the situations in which they played through the data through a detailed simulation of their vehicle software and predicted whether something bad would have happened if the driver had not disengaged. So their test drivers are trained to be very cautious, to take over if anything is just the slightest bit wrong, because they don't want to have crashes. So the test drivers take over more often than they probably need to for pure safety reasons. So they're estimating, based on the simulations, how many of these events would have led to some form of a collision. And their 2017 data shows about 5,600 miles, so a little less than 10,000 kilometers between critical events. That was a 9% improvement over their results from the year before. When we look at our human drivers in the US statistics, we've got about 2 million miles between injury crashes, about 100 million miles between fatal crashes. And it's hard to know for the property damage crashes, but the best estimate I could find was about 300,000 miles between crashes where there was some kind of damage on the vehicle. Big difference between that and 5,600 miles. And that's the best of the lot. A lot of the others are much worse than that, had many more frequent disengagements. In Berkeley, I had a lot of colleagues who deal with learning systems, thinking, well, we're going to use machine learning and that's going to solve all of our problems. Because the system keeps getting smarter and smarter. And at least when I go to the meetings and see people reporting results, they're thrilled if they get a 90% success rate in recognizing objects within a reasonably complicated environment. Well, if we're going to be comparable to drivers, so right now on highways, drivers are at about 99. I think there's 8 nines after that decimal point. And if you're in an urban setting, I think there are 9 nines after the decimal point. So how are we going to go from 90% to 99 and 8 nines? I haven't heard the answer to that question yet. So I kind of doubt whether learning systems are going to be the holy grail that's going to solve that problem for us. Then that gets us to our second big challenge, which is safety assurance. We got some significant traffic safety challenges because, of course, we've got all of these things that can happen outside the vehicle that affect the safety of the vehicle needs to be able to respond to. And I hear lots of people talking about 94% of crashes caused by humans, so those are going to go away, but nobody talks about the new crashes that are going to be caused by the automation itself. Automation gets into a circumstance the designer could not anticipate, doesn't know what to do, crashes. You get a software bug, never got exercised in the testing because you can't afford to do such an exhaustive set of testing that you're going to exercise every path, every combination of paths through through the software logic. You could have some undiagnosed faults, all sorts of failures on board the vehicle, and if you're talking about a level 4 automation system, you don't have a driver available to act as the fallback. The safety is dependent entirely on that software system. How are you going to certify that vehicle is safe enough? Whatever safe enough is, whether it's equally safe to drivers today or some factor safer than drivers are today. What's the combination of input conditions you're going to assess to make that safety determination? How do you combine test track testing, public road testing, and simulations to get to that point where you can say, yes, we are at least that safe? How much of each of those is going to be needed? And if you're going to depend on simulation, how are you going to validate the simulation? How do you know the simulation actually represents reality? Because if you're going to grind through all these simulations with an unvalidated simulation, that's pretty much useless. But that just told you what the simulation predicted. That doesn't tell you what's going to happen in reality. And how time-consuming and expensive is it going to be? I had an opportunity to hear some talks by people from Boeing about what they go through when they're developing a new airliner. This could be either a commercial airliner or military aircraft. And their experience shows the software verification and validation is half of the cost of developing a new aircraft system. So think of the cost of developing the airframe, the engines, the avionics, and all the software on the aircraft. You add that all up together, and then you've got to spend that much again to verify and validate the software. And that software is a whole lot simpler than the software that's going to be needed to do automated driving out on public roads. And that software is operating with continuous oversight by 2 very highly skilled, highly trained operators sitting in front of the aircraft. So the road vehicle automation situation is a whole lot harder than the aerospace situation. And in aerospace, we're talking billions and billions of dollars or euros to do that work for a single new aircraft platform. How are we going to do that for every new road vehicle platform? So we have some functional safety challenges.
Very quick question.
Yeah.
For the last point there, the cost change per year since that validation and verification is based on software, and software improves very fast. Have you looked into that?
I'm sorry, software doesn't improve by itself. People have to do stuff to it. Right.
The ability for the software to simulate something and the speed it simulates is rapidly increasing. So that should have a profound impact on the cost for validation and
That is
Look into that.
That is mostly a labor cost. You still have the labor of the highly skilled people who need to go through that process. I don't think that labor cost is going to disappear. This is not just a matter of grinding processing time.
I suggest we save the discussion
Yeah.
until after.
Okay.
Yeah. We have some challenges with functional safety. Some of these don't require new technological approaches. They're solvable with a lot of hard work. But I'd say some of them require some fundamental breakthroughs. System design errors, system specification errors, and software coding bugs. How are we going to nail those down? And know that those are so rare that the net effect is going to be at least as safe as human driving. So we have to overcome some of the limitations of the existing approaches, whether it's formal methods, which don't scale to something of this complexity, brute force testing, which is unaffordable because you can't run enough hours of enough vehicles to be able to build up that level of experience. And then if you go into learning systems, you've now got something non-deterministic. How do you know what it's going to do next? How do you verify that? Then there's also the need for robust threat assessment, sensing and signal processing. So you get to that zero false negative and near zero false positives. So robust control system, fault detection, identification, and accommodation. Topic we haven't talked about, ethical decision-making for robotics. How are these systems going to be developed in such a way that they satisfy ethical concerns and cybersecurity protection, since they are going to be attractive targets for people to want to attack. Overall, I'd say this is a lot harder than the commercial aircraft autopilot example because of things like how many targets you need to keep track of, how accurately do you need to know the location and the speed of all of those other objects, how much time do you have available to respond to an emergency. If you're in an aircraft at 30,000 feet, you've got tens of seconds to recover from a problem. If you're on a highway, driving at highway speed, you've maybe got a tenth of a second to be able to deal with the problem, and you have to do it on a platform that's a whole lot less expensive. So what does this all mean in terms of how long it might take to get to some of these higher levels of automation? And I said, this is a little bit like climbing Mount Everest. And I use that example because I see people making claims, oh, well, we've got 90% of this and we've got 99% of that. And I said, well, okay, if I'm going from San Francisco to climb Mount Everest, I got on the airplane and got off in New Delhi, I'm 90% of the way there. I covered 90% of the distance to get to Mount Everest. And then I took the connecting flight to Kathmandu, and now I'm 99% of the way to the top of Mount Everest. Isn't that great? And then I took a little airplane to get to the airport closest to the base camp. Well, I'm 99.9% of the way there. And then I get up to the base camp, I'm 99.99% of the way there. Isn't that great? Well, all the hard stuff comes after that. You haven't climbed Mount Everest until you got the 99 and all of those other nines after the decimal point. Because that's what you've got to get to if you're going to be equal to what the human driver is doing. So whenever I see these things about people predicting how close they are, you've got to think of it in these terms. Each of those last decimal points is at least as much work as the decimal point before. So when I try guesstimating when we might see these systems get introduced, I come up with this chart. The levels of automation along the lower axis and the different types of environments representing the operational design domains on the vertical axis. So the green things exist already. And I say the yellow things probably in the early 2020s, and then the light brown in the later 2020s, the darker brown, the 2030s. But to get to level 5, which means doing everything that human drivers are capable of doing, I put a very rough guess, 2075. Now, maybe it's 2065, maybe it's 2100, we don't really know. I've presented this chart in many different venues all around the world, and I've had lots of people from the vehicle industry in the audience when I presented this chart. And almost invariably, people will come up to me afterwards and say, yeah, we think that's probably about right. And this is often from people whose company CEOs have been out telling the media completely different things. There's a huge disconnect between the people who are actually doing the work on the technology and the people who are out there talking to the media from those same companies. So I got a lot of endorsements from people in several continents who've all said, yeah, that's probably in the ballpark. And this is to start. This is to get the first viable system that's out there in commercial operation. Then what happens is you start getting more and more vehicles on the market. How long does it take to get them through the vehicle fleet? Well, the fastest way is if the government says you got to put it on all new vehicles. We had that example with seatbelts in the US. It took 6 years to get to 90% of the new vehicles being equipped with seatbelts in all the seat positions. It took 22 years to get to 90% of the vehicles on the road being fully equipped with seat belts. And in the green curve, that's further off to the right, is the actual usage. So just because the system's on the vehicle doesn't mean people actually use it. So we've got this decades-long process of getting them into the market. And this is where there was a government push saying you have to do it. If we look at things that are optional, that don't require government push, this is some historical data, again, for the US market. New vehicles sold each year, maybe a little hard to read. The first of those is automatic transmission, then power steering, air conditioning, disc brakes, radial tires, electronic ignition. So the more complicated and expensive things took more years to go from being options on a few high-end vehicles to becoming standard on basically all new vehicles. This is new vehicles, so you still have to add a few more decades for the turnover of the fleet as the older vehicles that don't have the technology on board are retired. So we're looking at decades-long processes for these to take over. How do you reconcile all this with what you read in the media? If you read the media or read the blogs on the internet, you think everything's going to happen tomorrow. Well, the public is really eager to see the benefits of this, so there is a demand out there. The media are really eager to satisfy that demand, and we certainly know that science fiction is a lot sexier than science fact. So if somebody puts out a story that's got some really optimistic prediction what's going to happen, that's going to get a lot more attention than the more sober analysis that says, well, no, actually this is going to take a lot longer than that. We have a Silicon Valley phenomenon called FOMO, fear of missing out. So there's the bandwagon effect that everybody says, this is the next big thing, everybody's got to be on board, we all got to do it. And every company wants to maintain the image of being the technology leader. So as soon as one company starts exaggerating, then the other companies have to exaggerate in turn and put out things that make it seem like things are going to happen a lot faster than they're really going to happen. And the journalists who cover this in the media generally don't have the level of technical insight to ask the probing questions. They ask the hard questions about whether this is real or whether this is imaginary. Companies are also manipulating the media, and we can talk about that a little bit later, how that's happening. But basically what you get from the CEO and marketing people doesn't match what the engineers who are doing the work are actually saying. So given all that, I mean, this is sort of a dark story, and I don't want to seem too pessimistic, but when I talk to new students who are showing up in Berkeley who are eager to work on this, and they think it's going to happen really quickly, and I tell them that's going to take a long time, their first reaction is disappointment. And then I say, no, look on the bright side. You're interested in this. You will be able to work your entire career trying to solve these problems. And when you're ready to retire, like I am, then you'll still have more problems to solve for the next generation. You're not going to run out of things to do. So what should we do? I'd say first focus on implementing the systems that are technically feasible now so we can enhance their performance, get them better and better, and gain more public confidence in the technology. And that means level 1 and level 2 driving automation systems, which is, by the way, where I think we're going to see the bigger safety advances. Because with level 1 and level 2 automation, we've got the vigilance of the sensor systems combined with the vigilance of the driver. If we get to level 3 and above, we've thrown the driver vigilance away, and now we're entirely dependent on those sensor systems. And then we want to start developing those more highly automated systems within very well constrained operational design domains. because that's what's going to be necessary to ensure the safety of those systems. Keep them within a limited set of conditions, and then as the technology improves, gradually relax the constraints on the operational design domains, so the systems can start serving a wider range of transportation needs. And then in parallel, work on those fundamental breakthroughs that are going to be needed to get to the higher levels of automation under the less constrained condition. Because as I had a wise Silicon Valley person say a meeting about a year ago, this is not yet an engineering problem. There's still some basic science problems that have to be solved before we can solve those engineering problems. And with that, I thank you for your attention and look for some questions.
Thank you very much, Steve. Yeah, it is certainly a sobering picture you're painting here, but I hope there's still some enthusiasm in the crowd here. So, for once, I haven't prepared any questions because I'm sure there's going to be a ton of questions. So, who's first? I was expecting Ericsson to stand up.
Oh, okay. There you go.
All right. Thank you for a great speech, by the way. Very encouraging.
Please state who you are.
On negative thoughts. My name is Richard. I'm from the company called Combitech, the Saab group. We work a lot on aiding companies in getting into this transition here and solving the problems in a feasible way, of course. We talk about the level of autonomous driving. We always compare to the conditions of human driving, saying we can compare to the basic things, and all the way at level 4 or 5, we're measuring up to doing all the things that a human driver could do in general situations. My question, could it be of meaning to define the level 6 level of autonomy, where the autonomous driving system actually can surpass that which a human driver could? For example, driving at super high speed, underground or in water, or extreme accelerations or anything like that.
I think that sort of misconstrues what the levels mean. The levels are about the functionality of the system. So, and what is it that the system does versus what the driver does? So, as we go up through the levels, we've got different distributions of responsibility between the driver and the system. So when we get to level 4, the system is doing everything. That's all the levels are meant to do. Level 5 simply removes the constraint on operational design domain. It just says it can, at level 5, it can go anywhere under all conditions in which people drive. And the reason that was defined is because there were a lot of people trying to fuzz up this notion of the operational design domain, say, my vehicle doesn't need a driver, so that's the ultimate. And I said, well, but it only operates within this very bounded set of locations or very bounded speed range, so it's not nearly as capable as a vehicle that can go under other conditions. So level 5 is simply mean to represent it can do everything that a human driver can do under the full range of conditions. And I don't like the notion of trying to create another level because it doesn't fit within the overall scheme of what the levels are intended to mean. So you're simply talking about a more expanded operational design domain in the sense if you wanted to talk about a higher speed. So I don't think we would want to extend the levels definition to accommodate that.
Anders?
Anders Eriksson. About communication, we have DSRC in the US and ITSG5 in Europe, and I really don't see that as a communication system. I see it as a broadcast system because you just broadcast messages. You have no feedback channel. And when I think about highly autonomous cars, I think if they can share their intentions and acknowledge that they have understood, you can have this great efficiency improvements. But just broadcasting, then you cannot really rely on that anyone has received it and understood it. What's your opinion on developing the protocols?
Okay, I'm not a communications protocol person, but the way that is set up, you can broadcast that acknowledgement of receipt so that the sender can hear that acknowledgement if you wanted to get that acknowledgement. So I'm not sure that's necessarily a problem.
It's not in the standards.
No, and as I said,
Commission
the standards do need to be extended to add more messages.
Yeah.
And that's something that has just begun, the definition of the messages for doing the cooperation. So there hasn't really been a demand for it until now, but the working group just got established and has just started its discussions about what needs to be in those messages to enable the cooperative automation. So, yeah, I know the standard doesn't exist today, but it's under
that is
development.
where 5G gets in. 5G will be the technology to support this.
Well, and then there's a question of what is 5G? Because I've heard as many different definitions of 5G as there are people defining it. And at what point does it actually become available that it can actually be used by people? And how is this going to preserve the safety of these safety of life critical functions when it's also being used for very bandwidth intensive other functions? So there are a bunch of other questions like that when I hear presentations about it, to me, my vaporware alarm goes off really loud. And I'd be eager to see some technical substantiation on a lot of the claims, but my vaporware alarm really gets set off when I hear this is going to be everything for everybody.
Well, 5G is a long story, but there are a lot of concepts there, like network slicing to guarantee quality of service for mission critical information. So I think that the communication industry is working on these things, and it will be interesting to engage.
Unfortunately, in the US, the 5G concept has been weaponized as a way of attacking the DSRC system, because some of the companies involved in that are trying to grab the spectrum. And right now we have a problem of something that we have today that's being endangered by something that doesn't exist yet. And that is a huge concern.
Should we continue in the back of the room?
In regards to full automation 2075, how much? Assume.
Sorry, please say who you are.
If you assume that a city would legislate that 100% of the vehicles would be autonomous, so no non-autonomous vehicles would be allowed into the city, how much faster? Because then you don't have to include the complexity of dealing with cars that are driven by people. You only would have to deal with animals, bicycles, and people walking around, which is complex, of course. How much less complex do you think it would be to solve that in an environment with 100% autonomous vehicles?
Okay, well, first of all, that's not level 5, so that's a version of level 4, and that really depends now on the specifics of how would that operate. So, for example, how would those automated vehicles be separated from the other road users? What range of speeds would they be operating at? What forms of traffic control mechanisms would be put into place? We already have the example of Masdar in the United Arab Emirates, where they've got the personal rapid transit system that's connecting the different buildings. It's a level 4 system. It's been in use for several years. So at that point, that's already in existence. So it all comes back to what are the specifics of the operational design domain and what's the complexity of the hazard environment that the vehicles are going to have to deal with. So they're going to interact with the bicyclists and the pedestrians. Well, okay, how fast are the vehicles traveling? If they're traveling at 10 kilometers per hour, that's a lot different from if they're traveling at 60 kilometers per hour. So all of those things affect how long it would take to implement a system. So you can't just answer it in one context, but in particular, that's a level 4 thing, that's not level 5.
Stefan?
So, Stefan Justin, NEPS. Well, I don't want to ruin the parade or anything, but I would like to add the 9. Because you said typically you compare the mean time to failure with the mean time to an incident with a human driver. But if you talk to any police department really. I'm sure it's the same in the US as here. A sober, healthy, experienced driver typically has only 10% chance or risk of ending up in an accident compared to the other parties. And I don't think as an event we would ever be able to sell anything that doesn't compare to any of us in here.
Yeah, and it's a valid point. I was trying to set a minimum threshold.
Yeah, I know.
And I know I've heard some people say it's got to be 10 times as good as the average driver. In fact, the head of the Toyota Research Institute put that number out last year at our automated vehicle symposium. So, and yeah, there's actually a societal discussion needs to be had about that topic. That's not something that can just be decided by technical experts sitting in a conference room. That's something that needs a broader engagement with society in general about people's willingness to accept harm being inflicted by an automated system rather than by the error of a human driver. And the answer might be different in different countries too. Some countries might want to set a higher threshold than other countries just based on their societal norms. So my point of putting those up is saying it can't be less than this, and indeed the threshold may be higher.
More questions? Hello,
my name is Lindholmen, and I'm from Safer. I have a question. I've been working with the data and so on in automation, and when listening to the discussion in general in automation, there is a lot of talk that how the policymakers, their role in this, and they're not educated enough, or they don't understand it. What is your view on that? How can policymakers and the OEMs and so on, and other stakeholders work together?
Yeah, this is really difficult to educate the policymakers because the issues are so complicated, and it takes a lot of explaining to get to those finer points. I have a challenge next Tuesday. I need to brief people at the U.S. Congress about this topic area. I have 15 minutes. What can I convey to them in 15 minutes about the things that they need to keep in mind when they're trying to write laws to govern this? And at least the main message that I'm going to try to get across is do not assume that this technology is mature and ready to roll out right now. This technology is in its infancy, and there is a risk if we get irresponsible organizations putting systems out on the road before they're ready. They could ruin the market for everybody else. So, and we've already seen a little bit of this with some of the crashes that have happened recently that have started to get the public attention. People starting to get worried. Ooh, these aren't supposed to crash. And now we've got some people who got killed. Well, the expectations of the public need to be managed very carefully so that they don't get an inflated expectation of what this is going to be. They get a realistic expectation. And because we don't want to have a backlash coming and people say, oh, forget about that automation, that's too dangerous, we don't want to go there. In Silicon Valley, there's a frequent mantra, move fast and break things. Not a good idea when we're in this domain. We need to move very carefully to make sure we don't break things. And we need to have at least enough of a regulatory regime to protect the responsible people in the industry from the bad actions of the irresponsible people who are going to put things out on the road that aren't ready to be out on the road, or are going to mislead the public into thinking that the systems they have are more capable than they really are. So educating the public about the limitations of the technology and the real capabilities as opposed to the future imagined capabilities is a really big challenge.
Hi, I'm Steve Cook from Norconsult. I mean, what you're talking about now with the potential of a trough of disillusionment in the future for autonomous driving is rather interesting. If we look at VR from the promise of the 80s and 90s and how that disappeared for quite a long period, to come back again recently, and AI, which has also gone for a similar journey. Other things that we can do now to kind of manage that so that progress keeps being made at as good a pace as possible while the media goes through a disillusionment phase with the technology.
Well, part of this is trying to maybe damp out that disillusionment phase by managing expectations to be more realistic. So we get people to have a more realistic set of expectations, because when the expectations get to these greatly magnified levels, then the disillusionment is inevitable and is well justified. But we've got to get to the point where there is some realistic descriptions for people about here's what the technology can do under which set of conditions, and start educating the public and the decision makers about that, and then be able to demonstrate for them, because people develop all sorts of mental images of what this might actually be like that could be totally divorced from the reality of sitting in a vehicle and actually experiencing a system of operation. I mean, I deal a lot in traffic systems, and we've got people in the academic world who develop simulation models. Let's say something as basic as adaptive cruise control. And I look at what they write and say, this person's never even ridden in a vehicle with adaptive cruise control. The model that they've created of adaptive cruise control is totally unrelated to the way ACC works. And yet they're writing a simulation model that purports to predict what the behavior of the ACC is going to be. How are we going to get to realistic mental images of things if people don't have a way of experiencing it?
More questions? My former boss.
Maybe on your list here, I think this is very good balance. But this scientific modeling that you were talking about just now, don't you think that, as you said, it should be on the list almost because it's so important?
Oh yeah, the list, the full list is multiple pages.
Yeah. But on a short list, then.
Yeah. I think of it more in terms of producing realistic predictions of what the impacts are going to be, so people can do sensible benefit cost assessments, among other things, because they need to understand, especially on the public agency side, what kind of investments should they be making. I think I mentioned an example of people saying, oh, on-street parking is going to go away in the next 10 years. We're not going to need any on-street parking anymore because it's all going to be shared use vehicles that are going to be driving around continuously and they never need to park. And come on, that's nonsense. But if you get public agency people starting to say, well, we're going to eliminate all the parking spaces and put that into their plans, we're going to produce some bad outcomes. So we do need to get to the point where there's some realistic estimates of, well, what might actually happen at what future times, so that people can start making intelligent decisions about the future.
Claes Olsson, Abonir, we're talking about a long time here, maybe 50 years in the future. If you would put up a wish list, what breakthroughs would speed up this? What kind of things would you like to see?
Okay. First thing I'd really like to see is a high-resolution imaging radar system. I would love to have a radar system that could give me the objects and their rates of motion relative to my motion. I say that could help make a big move forward on the sensing side, so to deal with a lot of the sensing challenges. And I really want to see some breakthroughs in the software engineering methodologies. I mean, the way we create software these days is sort of like the way we build houses, it's just way too labor intensive and primitive. We need some more intelligent ways of developing the software so that we can get to a low enough rate of software faults that we can actually get to some of those safety improvements that we're hoping to achieve.
It's because you want to reduce the rate of faults in the software,
Yes.
thereby using more complex software.
Well, I didn't say more complex, I'm just saying
That's
different
right.
methods of developing the software so that you have a better chance of making it safe and of eliminating the bugs. And the bugs can be a different type, not just coding bugs, but specification errors. How do you develop the comprehensive specification for the software that's going to do driving under a very diverse set of conditions? What are the things that software needs to do? And how do you define that in a comprehensive enough way that you're not going to leave out something important, but in a simple enough way that it's actually feasible to do it? And people have been wrestling with software safety issues for decades. And there are examples going back to the 1980s, things like the cancer therapy machine that killed patients because there was a software bug. They eliminated mechanical interlocks to protect against overexposing patients, and the result was they had a software bug that caused patients to be overexposed to radiation in a machine that was supposed to be curing them of cancer. Several patients died because of a software bug. And we're going to have people die because of bugs in automation software as well. How do we keep that to be such a rare event that the total safety of the transportation system is going to improve?
Yeah, please.
You've only just, sorry, my name is V, and you just had one line in your presentation about ethics.
Yeah.
With the operational designs, each of the different companies can adapt it and they can use it, I guess, for themselves. But with the ethics, I think that will be something that needs to be standardized across all of them. Is there anything or anyone that's doing that at the moment?
It's just getting started, and actually some of our colleagues at Stanford University have been working on that the last couple of years. For a while, the ethics discussion got tangled up in the so-called trolley problem paradigm, which turned out to be sort of unproductive. People say, you got the decision, is your vehicle going to hit the group of 5 bicyclists who are wearing helmets, or is it going to hit the 2 bicyclists who aren't wearing helmets? It got nonsensical, and we had to get away from that and start thinking about how do you at least get people who are designing the systems to recognize that there are embedded value decisions in what they do when they're writing the software. And how do you make those conscious decisions rather than unconscious decisions when you're making value judgments about what strategies a vehicle should follow when it's dealing with a potentially hazardous situation. But it's really just at the very beginning stages right now. And we're going to have a talk about that at the Automated Vehicle Symposium in July. So we're just in email contact with our Stanford colleague who's working on that. So hopefully we'll get some update on how they're progressing.
But there's no central body that's leading the discussion at all?
No, and I think that's actually one that's going to be really interesting in terms of how much there are going to be national differences.
Yeah.
When you have different value systems in different countries, different societies, how's that going to play out? I don't know. I don't know. It's certainly going to make it more difficult for people in the industry if the vehicles have to be designed differently based on different value systems in different parts of the world. But I can cite an example from a country that I won't name that is planning some fairly aggressive demonstrations of some automation technologies, getting them out on the road quickly. And I asked the person, well, how are you going to deal with the adverse public reaction if somebody gets killed by one of those vehicles? And the answer was, you don't understand. We control the media. The story will never get out there. Oh, okay, that's different from the paradigm I'm accustomed to.
I'm going to exercise my moderator privileges by asking the last questions here, because we're going to close short here. But combining what you showed in your presentation, you mentioned the set of sensors required to be successful, and that included the wireless communication. At the same time, you mentioned that Waymo is ahead in this game, but to my knowledge, they're not getting into that application of wireless.
That's right.
Yeah.
Yeah. And actually, I had that discussion with them about 5 years ago because they're doing their testing very close to a location that we've got instrumented with a bunch of wireless communication, where we're broadcasting the traffic signal information. I said, wouldn't you guys love to use our traffic signal data? We're broadcasting it all the time. It's there for you to use. And there was a two-part answer. The first part of the answer is that would be great. That helps solve one of our most difficult problems because they said when they approach an intersection that their map database tells them has a traffic signal, they need to command the vehicle to stop unless they can verify they've got a green signal. And under some lighting conditions, that's not so easy to do because they're dependent on a video imaging system to do that. So they said, yeah, that would be great. But I said, on the other hand, we've got to develop something that we can use even when we don't have the infrastructure equipped with the communication technology. We want to be able to use it under a wider range of conditions. So that's the trade-off in having the communication. And I suspect to get to the higher levels of automation without creating traffic problems, it's going to be necessary to have the communications. Now that could be where there's a stronger motivation for the public authorities to equip their infrastructure with the communication technology as well.
Very good. Thank you all for coming. Thank you, Steve.